Let me ask you something. What if all the sensors in a car or robot were connected to just one brain? Sounds simple, right? But in reality, it doesn't work like that. And today you'll find out why. But first, what are sensors and their uses? Sensors are devices that detect changes in the environment and convert them into signals that can be measured or processed. They are everywhere around us, from simple home electronics to advanced automotive systems. In cars, sensors are used to monitor speed, temperature, fuel levels, tire pressure, and even help with safety systems like automatic braking and parking assistance. In electronics, sensors are found in smartphones, smart homes, industrial machines, and medical devices. They allow systems to feel the real world and respond intelligently. Now let's talk about cars. An ECU, electronic control unit, is essentially the brain of a specific system inside a vehicle or machine. It's a dedicated embedded computer that reads inputs, runs logic, and sends commands to actuators. Modern vehicles don't have just one ECU, they have dozens. There's an ECU for the engine, one for the transmission, one for the brakes ABS, one for airbags, one for the body lights, doors, and so on. Think of the ECU like a department manager. The engine ECU only manages the engine. The brake ECU only manages braking. Each one is an expert in its own domain. The ECU receives data, runs a control algorithm, usually a PID loop or a lookup table map, and outputs commands: open this valve, fire this injector, set this duty cycle. Now, why are they Sperry controllers? This is the key engineering question. Why not just plug all sensors directly into the ECU? Separation of concerns. The ECU is optimized for control logic, running fast loops, making decisions. Handling 30 raw sensor signals would overload it with low-level I/O work that has nothing to do with control. Real-time bandwidth. A sensor hub can sample sensors at high frequency, e.g., 10 kHz for vibration, without blocking the ECU's control cycle. The ECU only gets the processed result at a lower manageable rate. Signal integrity. Sensors are electrically noisy. Long cable runs, motor interference, ground loops. The hub is physically close to the sensors and handles shielding, filtering, and ADC locally, so only clean digital data travels to the ECU. Scalability. You can add or change sensors without touching the ECU firmware. The hub absorbs the hardware variation. Safety and redundancy. In safety-critical systems, ISO 26262 IEC 61508, separating sensing from decision-making gives you two independent layers. If the hub detects a faulty sensor, it can flag it before bad data ever reaches the ECU. Cost and silicon. A lightweight microcontroller in the hub does ADC and filtering cheaply. The ECU can be a powerful processor focused entirely on control. No need to provision it for raw I/O. The ECU shouldn't care how data is collected, only what the data means. The sensor hub owns the how. The dashed lines show the clean architectural separation. The sensor hub owns the acquisition layer, getting reliable data from the physical world. The ECU owns the control layer, making decisions with that data. They communicate over a shared bus, usually CAN bus in automotive, or SPI I2C in embedded systems, which is another reason independence matters. Either unit can be upgraded or replaced without re-architecting the other. And now, what about us? In a training setup, you can use two controllers. First, a sensor controller like an Arduino board that reads all sensors such as temperature, motion, light, or distance sensors. This controller processes basic data and sends it forward. Second, a main controller that acts as the brain of the system. It receives processed data from the sensor controller and then makes decisions, like turning motors on, activating alarms, or controlling displays. This setup helps students understand how real industrial systems are designed, where responsibilities are divided, instead of using a single overloaded controller. Now let's talk about something important in real development. A lot of beginners start with the Arduino IDE, and it's great for simple projects. It's easy, lightweight, and perfect for learning the basics. But when projects start getting bigger and more professional, we start to feel its limitations. That's why many engineers switch to alternatives like Visual Studio Code with tools such as Platform I/O. So why do we make this switch? First, organization. In professional projects, we don't just write one simple file anymore, we deal with multiple modules, multiple controllers, and complex systems. In Visual Studio Code, everything is structured in a cleaner and more professional way. Second, libraries. In Arduino IDE, managing libraries can sometimes feel messy or limited. But in VS Code, especially with Platform I/O, we can easily create our own custom libraries, reuse code, and manage dependencies in a much smarter way. And third, and this is very important, we can handle multiple controllers much more efficiently. For example, if we have a sensor controller and a main controller, connecting and managing communication between them becomes much easier and more flexible. We can structure the code like real embedded systems used in industry. So instead of being limited to a simple sketch-based environment, we move into a more powerful development setup that feels closer to real engineering work. In short, Arduino IDE is perfect for learning. But Visual Studio Code with Platform I/O is built for real projects. Sensors are the eyes and ears of any electronic system, but they need proper management to be effective. Using a dedicated sensor controller connected to a main controller improves performance, reliability, and scalability. Whether in advanced cars or simple Arduino projects, this architecture reflects how real-world intelligent systems are built. Understanding this concept is a key step toward becoming skilled in electronics, robotics, and embedded systems.